This exercise we have seen twice before in 2 other videos. However, we're going to solve the part A of the exercise using a different method right now, using the sequence networks method, which is a method explained in other courses, not in mine, and that some of my students who are taking those other courses chose to use in the exam. Nothing wrong with that, as long as you apply that correctly. Let's see how that is done. 3 identical single-phase 2-winding transformers with a ratio A N1 to N2 is 3. So this is N1 and this is N2. This voltage is 3 times this one, or this current is 3 times the current in X1. But this is not the way we're going to solve the exercise this time. They are connected as a 3-phase bank, as per the figure below, with the primaries in a delta, this one, and the secondaries in a grounded Y. The 3-phase unbalanced load connected to the secondary is represented by the 3 current sources on the right hand side of the figure. This one, those 3 sources whose values are given. The question A that we're going to solve in this video is determine the 3 line currents on the primary side. So determine this current, this current, and this current. Alright. If we're going to use the sequence networks method, the first thing we need to do is to identify the type of 3-phase connection we have, and that is a delta Y5. Is a DY5 connection. Let me write it down here. This is a DY5. And secondly, we need to identify which ones are our phases on the primary and the secondary. This would be phase A of the primary, phase B of the primary, and phase C of the primary. And given that it's a DY5, this is phase A of the secondary, phase B of the secondary, and phase C of the secondary. Positive sequence, right? That is a direction for choosing the names. And then what? Well, and then we draw the sequence networks for 0 for positive and negative sequence. That is the model of the 0 sequence. Observe that these models are single-phase models. Phase A of the primary, neutral of the primary, phase A of the secondary, neutral of the secondary. The ratio of that imaginary transformer has not N1 turns on the left-hand side. It is only one phase, so the number of turns is N1 divided by √3. And on the other side, this one, N2 turns. So the actual transformation ratio of that equivalent single-phase transformer is not N1 over N2, it's N1 over N2 divided by √3. That is 3 divided by √3. A for this one is √3. √3. This voltage is √3 times the voltage here. So this current is 1 over √3 times the current in the secondary, but that is valid for the positive sequence. We need to find the positive sequence current in the lines of the secondary. We need to find the 0 sequence currents of the secondary and also for the negative sequence. Here's the catch. In this equivalent single-phase transformer for the connection DY5 for the positive sequence, there was a phase shift going from the primary to the secondary of negative 150 degrees. That is negative 5 times 30 degrees. And for the negative sequence network, which is in this one, negative sequence, the phase shift had the opposite sign, positive 150 degrees. We need to determine those 3 currents. This one, that is the 0 sequence current of the secondary. This is the positive sequence current of the secondary, and this is the negative sequence current of the secondary. Find those three currents. Use those equivalent networks to find what is the zero sequence current of the primary lines, that is, of the system of currents, positive sequence current of the primary, and negative sequence current of the primary. But we need to find first those sequence currents in the secondary, and those currents are given. Those one, well, almost. They give us that this current, the current in phase A, is actually given by this source here, is 12 with negative 20. So let's write it down. Let's write them down. Let's move this a little bit down, just a little bit. That's about right. We say the three currents are the current for the phase A of the secondary is 12 with negative 20. The current B for the secondary would be this one. This current here is 1 FC is 9 with negative 100. And those are amps, of course. And phase C of the secondary, and this one up here, this current is IFA, that is 10 with 97 degrees. 10 with 97 degrees. Those are the three phase currents, yeah, in the lines of the secondary, and we use a transformation to find what are the zero sequence current of the secondary, the positive sequence current of the secondary, and the negative sequence current of the secondary, which are the ones that we will apply here, there, and on the zero sequence network up there to obtain then through the transformers what are the sequence currents of the currents in the lines of the primary. We use a transformation, right, and find those. Let me use the calculator, and those are the sequence currents in the secondary. 301 amps for the zero sequence here, and 979 for the positive sequence, and 188 for the negative sequence. Those are the currents that we will apply on the secondary of those single phase equivalents of the transformer. Those are those three currents. 301, 979 is this current, and the other one is 188. And then we apply the ratio. All right, we divide the magnitudes of those currents here by root 3, here by root 3. We add 150 degrees going from the secondary to the primary to the phase, and in this case we subtract 150 degrees to the phase going from the secondary to the primary to find those sequence currents in the primary lines of the transformer. Let's do that. Now that we have those three currents, the three zero positive and negative sequence currents of the primary lines, we use the transformation to find what are the actual phase currents here. Phase A of the primary, phase B of the primary, and phase C of the primary. So we just take those three sequence current values, use a transformation, and this is what we get. And doing that backwards transformation, we get those currents in phase A, phase B, and phase C of the primary. 626 with 132 degrees, 456 with 20 degrees, and 626 with 91 degrees, which are exactly the same current that we found in a much simpler way in a previous video. Thank you very much.